this seminar at ÚFAL. It's my pleasure to welcome here also our speaker, Dominik Macháček, who is PhD student at ÚFAL, and he will talk about his PhD topic, which is speech translation. Dominik told me that there will be a technical innovation today used in his talk. So please, Dominik, start with explaining this innovation, and then the floor is yours.
Yeah. So good afternoon. Thank you, everybody, for coming. I'm glad that you're interested in this topic. So my PhD topic is multi-source simultaneous speech translation. First of all, I want to tell very briefly what this talk will be about. Then I show you the live demonstration, and I also explain the topic or the new innovation, and so on. There are many topics in this talk, and here are some references to my PhD thesis. So we cover almost all. And for those who are new at this seminar, I'm planning to talk for 45 up to 60 minutes, right? And then we have more time for discussion, around 30 minutes after my talk. So long story short, speech translation is a technology for translating speech into text in another language. It can be either cascaded or direct. Simultaneous speech translation means that the source is available in consecutive audio chunks, as here in the columns in this picture, as audio wave. And the goal is to translate it at the same time as the source is being received. So it means that in the machine iterates, and after receiving every chunk, it can either listen for more input or translate. So it goes either right or down in this matrix, in this visualization. And the goal for simultaneous, or the reason for simultaneous processing, is that the results are available at the same time as the speech is being processed, so the users can interact directly in real time. And multi-source speech translation means that we expect two parallel language sources on the source, and the machine should combine both of them and achieve higher quality. Like here in this example, there is English source and German source, and we assume they have complementary errors in speech recognition. And the machine, if it's knowledgeable enough, it can avoid the errors and receive better quality in the end. And the model can look like this in this picture, like two separate encoders and decoders, and then average the presentations decoded. And this is the practical setup we aim for. So the main speaker here in this red circle, we suppose he speaks English. There is simultaneous interpreter, a person who speaks the same content in German. So he interprets the English speech into German speech, and the machine can follow these two language sources. And yeah, here on the left, there are the challenges that we suppose that are in this topic. So it's quality, latency, because the translation should be delivered as fast as possible. Then the challenge is that the sources, the original and interpreting, they are misaligned because interpreter is delayed. And also interpreting is not literal translation of the source, and the segmentation of the interpreter is different. We should balance the costs and benefits of multi-sourcing to be really beneficial. The data are challenged, the model and evaluation. And the plan at the top, it's very rough and general plan that we supposed to take. So we plan to apply text-to-text machine translation for cascaded speech, simultaneous speech translation, and supervise multi-sequence to sequence learning, maybe either find authentic data if possible, or use or synthesize training data for it, use translation across sentence boundaries, and apply simultaneous modes to it. So the basic steps are well known, but the challenge is to compound them. And in the results at the bottom of this slide, this task was very difficult and long, so it took me around 1 year to create evaluation data. Then I analyzed interpreting, I did survey, and I analyze it on the evaluation set. And I investigated multi-source model in a simplified setup, and I set background for the next steps, which is I focused on the human evaluation in simultaneous speech translation mode, and then on metrics, and I implemented whisper streaming, which is a tool that I'm demonstrating now. So the task is not yet done yet. We don't have practical application for multi-source speech translation, but we can continue. And now the demo. At the same time as I'm speaking, then the machine follows my speech, and later when you can speak in the discussion, it will follow you as well. You can open your web browser on your design, on your devices on this link. It's quest ms.mff/eliter/demo, and there I can show it. Yes, if you notice that sometimes something doesn't work, you can refresh the page and it will start again. So here at the column, okay, so at the column EN is translation from the speech in the language that we are speaking into English. In the column ASR is speech recognition in the original language. Yes, sorry, I'm just inspecting where are the translations. So I try to start again. So I'm starting to speak again, and where are the translations? I hope they come, or if not, then just, oh yes, there are translations now. So in the other columns, there are around 43 languages of translations. You can select the one that you're interested on your device. So let's look at these. And the translation is from English. And there's also automatic detection of the language. So when I switch to Czech, teďka budu chvíli mluvit anglicky a uvidíme, že v tom sloupci ASR bychom za chvíli měli vidět češtinu přepsanou. Je to tak? Jo, je to tam. A ve sloupci EN bychom měli vidět překlad z mé češtiny do angličtiny. So I switch back into English. I suppose that this tool would be available for our discussion in our most preferable languages, because usually after Monday seminar we discuss in English because it's our common lingua franca, and we have foreigners among us who don't know Czech, so all of us speaks English. But if we all agree and we can test the feature and have discussions cross-lingually. But it's risky because we haven't tried this before. So in worst case, we just switch into English and won't understand each other and realize it later. Yeah. Yeah, and this is how the demo can look like. Yeah, and yeah. And the tool that is running in the background for the speech to text translation in simultaneous mode. It's called whisper streaming. It's the tool that I implemented as demonstration in the thesis. And the new part that is not in the original paper is that there is voice activity controller. It means that when I make a pause 500 milliseconds, then translation starts from scratch. So if I make a pause like this, and you should see the transcript very soon. The language detection is there and so on. And the streaming policy is with local agreement tool, which is result of research of our colleagues. And the whole tool is wrapped in the ELITER pipeline, which we had in the ELITER project, European Live Translator, in past years. So now let us have a look at the next topic, motivation. So the most expected reason for multi-sourcing from the original and interpreter are the quality gains, because there can be word search disambiguation. There are ambiguous words which can complement from the two languages. For example, German word Schloss is ambiguous, and the German word, the English word can be disambiguated, or the English word alien is ambiguous and German translation can disambiguate it. And also because the source is speech, then the speech recognition errors, they can also be complementary. The other expected benefit that there doesn't have to be any human interaction for detecting and switching the optimal source when there are multiple options. For example, in these setups, in the ELITER project, in the EuroSci Congress, they had English original speech and interpreters into German, French, Czech. And there was speech recognition in these all languages and then translation into English. So there are 1, 2, 3, 4 options of English sources. And the goal is to translate the English into the 40 languages. And it's very difficult to decide in real time which source is optimal at the moment. So the machine should optimally switch it on its own. And next reason is that it's possible to have best from both options, because translating from the source, it can be more word for word, so therefore more faithful. On the other hand, the disadvantage is that it can be too complex to perceive for the target user, especially if the speaker hesitates or speaks unclearly or very slowly. It can be too disruptive. So the interpreters, they usually talk briefly and briefer and simpler than the original, because they also need to catch up. And they simplify the message. They also sometimes apply intercultural transfer that is very tricky or difficult to apply on the original source. The disadvantage of the interpreter is that it doesn't have to be reliable. There is also delay in interpreting, while the translation from the source must be fast. And it's possible to control the acoustic conditions of the interpreter, while from the original speaker, the speaker usually has enough worries to think and speak about the content, and it's sometimes difficult to tell him, please use the microphone properly, or make pauses, or speak clearly, or speak slower, and so on. So the interpreter is possible to control more in this way. But the risk in the red is that we know little what do the target users actually need. And it may happen that in one audience, in one set of users, various people have various preferences or needs. The next risk of this research is that there may be no improvement in practice. It may happen that one source may be always good enough, so the multi-sourcing will would not help, or that more sources will be never good enough, especially when the recognition quality will be too low. So in very general, we plan to exploit the benefits and avoid the risks, and use the supervised multi-sequence to sequence model. And here is one example where the additional language actually helped. This is from chapter 8 from my thesis. So in a basic system, we have the English transcript of the sentence here in the middle set of lines, and there's incorrectly recognized word funded or founded, while in German this word, the red word in English is wrongly transcribed, and the corresponding German word in green, it's correctly transcribed. So when we have translation only from English, then the Czech word is wrongly translated as financováno, while when we have multi-source model that takes both these sentences, then this word is correctly transcribed. So this is one cherry-picked example. And now I will talk about specification, what I focused on in my research. So I already talked that this is the practical setup that we aim to create the application for. I focus on primarily on the text-to-text machine translation part in a cascaded speech translation. And the cascade means that there are some underlying components, the speech recognition called ASR on this slide, which transcribe the speech in original language. And then there is another component that adds punctuation, the punctuator, and then another component based on the punctuation can segment the full sentences and then put them to machine translation, which is trained for full sentences and translate them. And we assume that, or we don't assume any output modality, but in reality it can be either text or speech. So we primarily focus on unspecified modality, and if it matters, we suppose it's text because we have experience with text as output modality. We also focus on the long form monologue because it's authentic and challenging use case. So the challenge is that the speaker speaks longer utterances in one sequence, and there are no clear sentence boundaries. And the speech can be read or spontaneous, it can be fast or slow. There can be hesitations and false starts. The speaker can speak some uncommon language variety or so-called accent. And it's possible that there are some noise. So we primarily don't focus on these challenges except the sentence boundaries, because we assume that other components in the cascade will resolve it. But it can happen that the other components, of course, they influence the overall quality. And I also want to explain what is simultaneous interpreting. So it means that a person mediates the foreign language communication, and it means the spoken communication in real time. The simultaneous interpreting, it creates only small additive latency, while there is also consecutive interpreting. It means that this main speaker speaks for some time, then stops, and then there is the turn of the interpreter. So we're not focusing on this case. And I'm also showing this slide because the interpreters and translators, they really like to distinguish these two terms, because the translators translate text, while the interpreters, the spoken or sign language. Yeah, And there are two approaches to simultaneous speech translation. One is retranslation, the other is streaming. So in retranslation, we retranslate from beginning of the sentence each time we have a new update or new content, and the machine can rewrite and append. While in streaming, the streaming method alternates between reading from speech recognition and translating. No rewrites, only appending. And so there are trade-offs in these two applications. In retranslating, it's latency versus stability, because when the stability is low, then the user must read what read moment before. So the content fluctuates. For example, here with delivering this forward, the second word is retranslated. So it's undesirable effect, but the quality in the end is always the top. It's like if the whole sentence was available at the as full at the beginning. While in streaming mode, there is a trade-off of latency versus quality. We can postpone processing for some time, so it has enough context to continue. But and if we don't wait enough, then the quality drops. But the stability is stopped because we are only incrementing, only appending to the end. And in our demonstration, we use streaming approach for ASR and for English speech to text, while we use retranslation for translation from English. So you can notice it. So now the next topic of my work are the data. So I created the evaluation corpus ESIC from European Parliament. And in this corpus, there are 3 parallel languages: English original, German simultaneous interpreting, and Czech simultaneous interpreting. And there are also parallel revised text translations. In this corpus, there are 10 hours, 370 speeches with word level timestamps. So the preview can look like this. So this audio track is the original, and there are revised translations, and with the word level timestamp is that, for example, this word European, it's uttered in this segment of the speech. Here we have the Czech interpreting. We can notice that it's somehow delayed. And here is German interpreting. And in my thesis, I described the process of creation of this corpus. Originally, I downloaded lots of data from European Parliament because I realized it's a very useful resource. And in the period 2008 to 11, it published translations, parallel translations in all 23 EU languages in the time, and simultaneous interpreting also in all these languages. So I'm just highlighting that we have this data at ÚFAL and we can process it for some research. But also 1 year after I created this work, there was Vox Populi corpus from Vank et al. From the researchers from Meta, I think, and they processed the same data, but they focused on the scale and less on the manual transcripts. So the Vox Populi can be used as well for the same analysis, but I'm not sure whether they have links to original documents. In my corpus, there are the whole documents. Well, so next topic, the analysis of interpreting. So in our paper, Lost in Interpreting, from 2021, we analyzed the ESIC corpus. and compared the simultaneous interpreter into translations, and we realized that it's by 13% shorter than offline manual translations on English to Czech, and when we count the syllables, because the syllables are universal units, kind of. We also compared we measured how simple vocabulary the interpreters use, and we found out that the interpreters use words with significantly lower rank in corpus. So when we compare the words from the translations from one to many based on the occurrences in a big corpus in Czech, then, and we have a set of these ranks, that these two sets, the set from the interpreters interpreting and from translation, they are significantly different. And we also measured the latency of interpreting, which is on average 4 seconds behind the source. And we also measured that machine translation following interpreting is approximately 9.8 seconds behind the source, because it was some retranslating machine translation from 2020. Today it can be different, but we realized that this result is similar to relay interpreting, because sometimes when it's impossible to translate one language directly into another, then there is an intermediate interpreter. So there are 2 passes of interpreting, and they add latency, but people are used to this twice double latency. So we assume that if a machine follows interpreter and has this double latency, it can be acceptable by users as well. So we can focus on the research of multi-sourcing. We also did a survey of interpreting strategies to analyze what could be challenging when applying interpreting as secondary source. And the challenges are the segmentation to sentences, because the interpreters are instructed, or they work regularly, that they prefer simple sentences which don't have many long-term dependencies. And so there's not direct one-to-one sentence alignment as in text-to-text translation. They also use the principle of language economy, so what they produce should be short and simple. So they reduce redundancies. For example, one very long and polite welcoming phrase with 20 words, it can be interpreted as single word welcome. This is so they can catch up. They also use generalization. For example, they can interpret pets instead of cats and dogs because it's short, or when they forget translation of some word, or when the name entity doesn't matter and the foreign audience doesn't know it anyway, like the next example that you will see. And sometimes they also prefer specific grammar constructions, unlike in translation. For example, English and Japanese, they have quite different word order. It's SOV versus SVO languages. And the interpreters usually use some passivization or some grammar constructions that help them to overcome this difference. So this is the results from this paper. And here is one example from the slides of Andrei Boyar. And here you can notice the segmentation to sentences, removing the redundant hesitations in the red, and the word halvang. Yeah, and although it's much simpler. And this second comparison is not repeated, comparing and comparison in the end. So this is challenge to investigate or to be Yeah, so the next topic, the robustness of multi-source, robustness to the speech recognition noise of multi-sourcing. So we created a very basic multi-source neural machine translation model. It's called light averaging. It was originally proposed by Firat et al. And it means that we train one model for English to Czech and another model for German to Czech. These two models must have the same output vocabularies or the target vocabularies here. And then we basically ensemble them. So we encode and decode, and then we average the output probabilities before generating the next token. And we compare this approach to early averaging, which means that we would average the representations of the encoder, but light averaging was giving better results. And we can apply this model only in simplified setup. It assumes that the source sentences are sentence aligned and parallel. And if they are not parallel, then it will get worse results, of course. But we use it to study the robustness to transcription noise, because we don't have speech recognition systems that would deliver various levels of word error rates, then we synthesize such systems. We use a model from Martucci et al. And this model, it models the edit operations on GOLD and ASR transcript pairs. So it learns to shuffle some homonyms. For example, this president and present, or it can shuffle 8 as a digit and 8 as a verb. So it's realistic, and we adapted it so that it can generate any level of word error rates. And we inserted these errors into text test set. But of course, I already told that, and we use text translation. So this setup is simplified so far, but it helps us to show the robustness. And here are the results. So we evaluated the model with all pairs of word error rate levels. So here in the columns is the level of errors in English source, and in rows it's the level of errors in German source. And here in the first row are the results of the single source system. So here it's English only. This first column is German only. And in the middle are the results of the multi-sourcing system. And we can notice that in the area in the middle, around the diagonal, the BLE scores are higher of the multi-source system. So and then we implemented, we adapted the model for simultaneous mode using the streaming approach and local agreement to streaming policy. And we can also see that here on the diagonal, where the blue line is above the two others, the multi-sourcing system is better than the two single-sourcing ones. But I didn't say that the multi-sourcing model is better, but that it achieves higher BLE scores. And we also investigate other metrics, and we also notice the effect of the source language of the reference. So here we can see the results with character F scores on the ESIC. On the ESIC test or def set, the reference is the translation, and it was translated originally from English. While here on the News 11, when the reference originates from 5 languages and it's balanced, then it doesn't favor English. And also we have here 3 references translated from German, and in this table there are the offline modes in the offline mode, and we can notice that it's vice versa. Here the single sourcing from German is better than in the ESIC, where the original language is English. Yeah, and here it is balanced, so the multi-sourcing is better. So we assume that these aspects of the source language of the reference should be taken into account, and in the end, the multi-sourcing can be used to improve the translation, And next, in another chapter in the dissertation, we use the same model, but real ISR outputs. Then we had the real ISR outputs with the top performing ISR systems. So the best one that we found for English and best one that we found for German. And we perform human evaluation, and the results are here. So the total plus is the number of occurrences in 79 sentences where we noticed something that was better than in the alternative. So better translated expression. So we conclude that but in the multi-sourcing model, we found 28 of expressions. So we conclude that multi-sourcing is able to benefit, but it brings also more issues. So we should investigate better the model. For example, use multi-sequence model and not light averaging, because although the model used aligned sentences, but they probably were misaligned, and also in the interpreting is not literal. So the multi-sequence model can be more robust to this. So this can be investigated in further work. And then for the further work, I had a question to investigate, because in ESIC corpus, there is Czech interpreting as a reference and translation as a reference, and we were not sure which one should we use. So we focused on human evaluation of simultaneous speech translation, and I have the slides from the conference, and this whole presentation takes 15 minutes, but I will take only the first part because it's not necessary. So the long story short of this work is that the machine translation metric were not originally designed for simultaneous speech translation. So in this diagram, it's an approximation. We can consider segment level machine translation, the innermost bubble as one task, where the main goal is the machine translation quality in the segment level. But machine translation, we can assume it's superset of this task, which has some more challenges, and they are the document level phenomena, the coherence between languages, etc. And then speech translation, the next bigger bubble, has the same challenges as machine translation, plus the challenges of speech source as speech source modality. And simultaneous speech translation has even more challenges, and it's the simultaneity. It means that the latency, and also that the user who looks at simultaneous speech translation outputs, they see them for limited time, so they read it only once and then they focus on something more. They also cannot return to it as in text, and we also assume that one evaluator sees the content only for the first time and only once. So this is different than in machine translation evaluation. And next reason for this paper is that, however, that the machine translation metrics are used for assessment of simultaneous speech translation quality along with latency. So the current standard in simultaneous speech translation is that one system has a parameter that controls the latency and quality, and it's evaluated with different levels of the parameters, and then it's put into plots like this. So one line corresponds to one system, and the points are the points where the system was evaluated. And the goal is to be at as much in the left, which means low latency, and as much as at the top. So this blue system, it means it's better than the others because it's higher and more on the left. Yeah, and everybody assumes that using machine translation metrics in this evaluation is reasonable, but there was no evidence. So we brought this evidence because we compared the machine translation metrics to human ratings of simultaneous speech translation, and the form of human ratings, it's continuous rating. It's end-to-end, it's framework for collecting speech-to-text evaluation of users in end-to-end. So there is a simulated session of simultaneous speech translation where a user follows a video or audio document with generated text by the system, and he or she are instructed to continuously press the rating buttons 0 to 4 or 1 to, it doesn't matter, there are 4 buttons, and they should capture the current satisfaction with the outputs, and they can be instructed to capture to focus more on adequacy as in IWSLT. This continuous rating was first proposed by Ondřej Bojar, and we implemented it in the paper that is referenced in another slide. Then in David Jaworski's work, it was validated on questionnaires and bilinguals. So there were factual questionnaires that we compared to continuous rating, and we realized that the bilinguals we realized that continuous rating, when the evaluators know the source language, are reliable. And in IWSLT 2022, the continuous rating was collected on the competing systems. There was a competition of simultaneous speech translation systems. So the ratings were collected but not analyzed much in detail, and that we did this in this work. So in summary, I will skip the rest of this presentation for the favor of the next ones. You realize that the machine translation metrics really correlate to continuous rating, and we can take this as a fact that they are reliable for assessing the quality of current simultaneous speech translation systems. And we also found the most correlating metric setup, which is COMET. And also we analyzed we found the most correlating way to align the candidate to the reference. And next topic is turning whisper. It's the whisper streaming. So in my experiments on multi-sourcing, I used offline ASR systems. Offline, it means that first you record audio and then you process it. While in streaming mode, we want this at the same time. There was a model Whisper from Radford at Altera. It's trained on lots of data and on many languages, on 96 languages, and it achieves the state of the art in speech recognition in these all languages and in translation into English. But originally, it was not prepared to support the real-time processing. There are only some implementations on GitHub that said it's real-time, but what did they do? It was that they recorded 30-second segment chunks and then they process it with Whisper, but the quality must be low, especially when you don't do language agnostic segmentation. You can cut a word in the middle, and the latency, of course, is very high. It can be on average 30 seconds at least. And at the same time, there were methods how to convert for streaming methods. It means how a model can be used in simultaneous mode. And for example, if you use the local agreement streaming policy, which was proposed by Liu at Altera, and then in Peter Polak's work, he compared many similar methods, streaming methods to local agreement, and he found this one as the most effective or the best performing. So we use this one, but these methods, they usually were described in the research paper, and there was no tool where Whisper and the streaming methods were available at once in one simple tool. So I implemented it together based on demonstration that Peter Polak created, but his code didn't support long form processing. It means that in the research papers, they usually focus on segmented speech. It means that there is some externally information where are the sentence boundaries, but this is not true in real-time application like on this talk that we're using. So I implemented it together, and it's a demonstration. It's only system demonstration, so there's no new result of this work. And do we have time, or should we switch to discussion? I can, in the next part of this, I have explanation how this works. So I can go through this, or we can stop. So I'm deciding for us to skip it. Do we? Okay, but we have few more topics. Yeah, this is why we use local agreement. And local agreement has self-adaptive latency. It detects on its own whether it should take the risk and produce the output, and then use the produce prefix as the prefix in the next iteration, in the next updates, or whether it should rather wait. So it's very effective tool. And the way how we make real-time processing possible is that there is a fast implementation of Whisper, which on GPU, 30 seconds of audio, it decodes in almost 1 second. So in this way, we are able to catch up real time. And there's a parameter which says how long is new part of audio that we're processing. It's either quarter second, half second, or 1 second. In my current demo, it's 1 second, or whatever received. Because when the processing loop takes longer, then we process the part that was received from previous iteration. Yeah. And here is evaluation on English in green, on German in orange, and in Czech in blue. And this is speech recognition quality versus latency of the system. And we realized that there is, if we would process the whole document or the whole audio in offline mode, then the quality would be 1.8 word error rate better in English. So it's here. And there's also this gap in. So the streaming in real-time mode, in real-time mode, we sacrifice some quality for lower latency. And there's also the trade-off of, again, the trade-off of quality and latency. And we also found out what part of latency is caused by implementation and hardware. It's 2.5 seconds. And the remaining part, 1.7 seconds of latency, is caused by the whisper's ability to model the language and also by the language complexity. And the total in real time or in total is 3.3 seconds with this highlighted setup example. Yes, and we achieve good quality. Yes, this is from previous presentation. Yeah. So, yeah, so whisper streaming is one result of my work. It's nice demonstration, and there are references on these slides. And now the summary. Working for 1 hour almost. So in conclusion of my work is that we investigated methods for multi-source simultaneous speech translation from the original and simultaneous interpreting. The main finding is that we sent the foundations for making this practically usable application, but we experimented with the basic model in simplified conditions, and we analyzed the weaknesses and proposed further steps. But more work would need to be done to make the application working and usable in real-life conditions. The main contributions of my work is the ESIC evaluation set, the analysis of simultaneous interpreting, the study of multi-sourcing robustness to speech recognition noise. Then we compare the previously untested assumption that the machine translation metrics can be used in simultaneous speech translation evaluation and the whisper streaming tool. And we also, our work is continuing because we have increment project. It stands for interactive cross-lingual minutes. So in this project, I can continue with multi-sourcing research, and I can also develop further ideas like prompting in Whisper and live post-editing. And these ideas I found thanks to my PhD research. So now, yeah, so this is the end of my talk, and now I'm available for discussion, and Ondřej Bojar can tell us more about increment project very briefly. The microphone is over there.
So thanks, Dominik, for the summary of your work and also for the chance to mention this follow-up project. As Dominik said, this is interactive cross-lingual minutes. It's a follow-up project of Eliter, which I was presenting some years ago here. And one of the tasks was not only to translate live what people are saying across languages, but also to take notes for participants in a meeting. And there is a follow-up EU project that we are not part of. It's called UTTER. It's coordinated by, I think, Amsterdam and Edinburgh. Colleagues are also within the UTTER project. And we applied for some third-party funding from that. So we got 9 months covered, in which we should collect more meetings and now multilingual meetings. So the goal of this increment small project is to collect meetings where people would, in the extreme case, be discussing so that everybody would speak their mother tongue. The minutes would be created and editable by anyone in any of the involved languages. And at the end of the meeting, everybody would get home with the minutes in their mother tongue again, so that it would be natural for everybody to use their language, the language that they speak best, and still talk to all the others. And it is, this is, as said, the extreme target. We can go anywhere, but we simply should have more languages in a meeting. So the offer that Dominik had at the beginning of the seminar, that we would lead our discussion across languages, would actually be a nice example of such a cross-lingual meeting. And we are complementing a tool which was already created here and defended as a bachelor thesis by František Kmiec, now master student at ETH in Zurich. So you see a screenshot of that Minuteman tool that would be, of course, available to anyone who would contribute to the data set collection here. So in the Minuteman tool, the transcript using very similar, maybe whisper streaming directly, or maybe just like some update of the Dominik's code. In the left-hand part, it is recording the transcript of the minutes of the meeting. And every now and then, a part of the transcript gets summarized into meeting minutes. So it's individual points in the right-hand side, which somehow summarize what has been discussed and what has happened. And it is an editor which allows everybody in the meeting to correct what the ASR has maybe misunderstood in the transcript, or what the summarization has miscaptured, misrepresented. So both the transcripts and the minutes are editable live by anyone in a shared editor. And if you fix the ASR, then the corresponding summary gets recreated. If you fix the minutes, of course, it stays as the humans did it. So at the end of the meeting, ideally you would have the minutes corrected by other participants live again. So if you hit once more at that, then there will be an invitation for everybody who runs their meetings with students or colleagues or whatever. If you would be so kind, and if you would run some of your meetings with our tool, if it's a remote meeting, then it's ideal because we can already separate the channels. And then you can, of course, make use of this tool to get the summary right away. But primarily, we would then, with the funding from that small project, the increment project, we would transcribe or correct the transcriptions of your meeting and include it in a collection of meeting transcripts for such a cross-lingual summarization experiments, and maybe a shared task, similarly as we did in ELITER. Of course, all the personal data are removed. At the same time, traits of your personality will remain there, because it is the discussion that you will have led. So it's technically it is like GDPR free. The data is okay, but we always give the preview of the de-identified people to all of you who provided that data, to the respective data providers, to confirm that it is fine to release it. Your name is not included, but someone could recognize you if they knew you. So that's it. So please get in touch with us if you would be happy to share some of your meetings, and if you would like to also try running these meetings across languages, which could be fun and could make our world like more diverse in practice. Thanks.
Thank you for the thesis presentation and also for the presentation of the project and beyond. So time for questions, comments.